In this example, we have a bird that's diving at the ground. Its initial velocity is 0 meters per second, and it starts at a position of 0. After 10 meters, it follows a curved path that has a radius of 4 meters. We want to know what the acceleration is at 3.5 seconds. We also know that the tangential acceleration of the bird is 2t meters per second squared. Well, we have an equation for our tangential acceleration. And we know that the magnitude of the acceleration is going to be equal to the normal squared plus the tangential squared, square root of all of that. So if our tangential is 2t, then at 3.5 seconds, my acceleration is 7 meters per second squared. So that's one portion of our equation, but we need to find the normal acceleration. The normal acceleration is the velocity squared divided by the radius. In this case, our radius supposedly is 4 meters as long as at 3.5 seconds we're into this curve. If we're not into that curve, then we don't have a normal acceleration. If we are at 9 meters, for example, there is no normal acceleration, and our acceleration magnitude would simply be the tangential acceleration. So at some point we're going to have to determine whether or not we're still in this curve or if we've come out of it or are before it. So to get our normal acceleration, we're going to need to know what our velocity is. To find our position, we're going to need a position function as well. Well, we know that acceleration is the derivative of the velocity with respect to time. Therefore, acceleration times the change in time is equal to dv. We have a function for our tangential acceleration, 2t, and we plug that in for acceleration. So 2t dt is equal to dv. And if we integrate both sides from a time of 0 to t, we're going to do it symbolically first. And a velocity, we started at rest, and we're looking for a final velocity. Integrating this, we're going to get t squared evaluated from 0 to t is equal to v evaluated from 0 to v. Or t squared is equal to v. In this case, our velocity then becomes 3.5 squared, which is equal to 12.25 meters per second. So there's our velocity and our tangential acceleration. Now, before we plug this into our normal acceleration equation, we've got to find out what our position is. So we need an equation for position. Well, if our velocity is equal to t squared, and we know that velocity is equal to ds dt, therefore t squared dt is equal to ds, and we integrate both sides from time 0 to t and from a position 0 to s, and then integrating both sides we end up with t cubed over 3 is equal to s. And if we put in our time, which is 3.5 seconds, 3.5 cubed over 3 is equal to 14.3 meters. So we know from 14.3 that we have gone beyond the 10 meters that the bird initially dropped. Now we've got to find out if we're still in this curve or if we've gone beyond the curve. To do this, we know that position is equal to the radius times the angle in radians. We've got a half circle, so we've got pi radians, and our radius is 4. So 4 times pi equals 12.57 meters. And if we add that to our 10 meters that we initially had, then we get 22.57 meters. So 10 is less than 14.3, which is less than 22.57. So we are in the curve. Now we can go back up to our normal acceleration and plugging in what we know. Our velocity we determined was 12.25 meters per second. So 12.25 squared divided by our radius, which is 4 meters, gives us a normal acceleration of 37.52 meters per second squared. Now we can come down and get our magnitude of our acceleration, which is equal to 37.52 squared plus our tangential acceleration, which we found to be 7 squared, and take the square root of all of that, and we'll get a magnitude of acceleration of 38.2 meters per second squared, which is our answer.